conservation of probability current. The conservation of probability states that the total probability of finding a particle in a closed system is always 1. It implies that the probability distribution of the conserved variables such as momentum, angular momentum, charges, and so on over the entire ensemble should not change. It means that the probability cannot be created or destroyed, and it is mathematically ensured by the normalization of the wave function. So the total probability is always conserved over time as the system evolves according to Schrödinger wave equations. This is similar to how the electric charge is conserved in electromagnetism. The wave function is a measure of probability of finding the particle in a certain region of space, and the particle is certainly to be found somewhere in space. It implies that the probability integral must be equal to 1. We know that the wave function must be normalized to unity. It is true for all the time, since the particle will certainly be found in the particular region. This change in probability of finding the particle with respect to time is known as probability current density. Hence the probability P must be conserved, that is dP by dt equals 0. It implies that P is constant, P is conserved. We know already that P of R is defined as psi star psi, the product of normal wave function and its complex conjugate. So differentiating equation 1.59. So this is equation 1.59. So we are going to differentiate this equation. And it gives us partial d by dt integration P of R d tau. Because your P is a function of R comma t. So that's the reason that we have done with a partial differentiation. So which is equal to partial d by dt integration psi star psi d tau. Psi also depends on R comma t. Now, as I said just now, the psi depends on both R comma t. We are going to differentiate the right hand side with respect to time. So keeping psi star as constant, you are going to differentiate this, plus keeping psi as constant, you are going to differentiate this. So we will have this equation 1.61. So integration psi star d psi by dt d tau plus psi integration psi partial d psi star by dt d tau. Now let us take time dependent Schrödinger equation as given by this I gets cross d psi by dt, which is nothing but your E psi, which is equal to kinetic energy part plus potential energy part. Now take the complex conjugate of equation 1.62. So wherever you find I, you'll have to go with minus I. So psi becomes psi star, and we can obtain equation 1.63 exactly like this. Now here, very important thing is V is an operator. Potential energy is an operator. When you are going to take the complex conjugate, it becomes V dagger. So this is called a dagger. That is Hermitian conjugate. Psi becomes psi star, whereas V is the operator. We should write only V dagger. This is Hermitian conjugate. Now multiply equation 1.62. So this is equation 1.62 by psi star. So we will have I gets cross psi star partial d psi by dt, which is equal to minus h bar squared divided by 2m psi star del squared psi plus psi star v psi. Now multiply equation 1.63. So this is equation 1.63 by psi. We will have this equation 1.65. Now subtracting equation 1.65 from equation 1.64 we have. So we'll have to subtract from here to here. So this becomes plus. So your left hand side is pulling I gets cross common out. We will have I gets cross psi star d psi by dt plus psi d psi star by dt, which is equal to right hand side. Just take the last term. Last term goes with psi star v psi minus psi v dagger psi. Suppose we are going to consider V equals V dagger. That is, the operator V is Hermitian. That means we will have real values. So in that case, the last two terms, both the terms will get cancelled. And this term minus h bar square divided by 2m psi star del squared psi, and it will become plus. I have pulled one minus I out, so this will become minus I. So we have taking common term out, minus h bar square divided by 2m psi star del squared psi minus psi del squared psi star. So bringing this IH cross to right hand side. So we have IH cross here to the left hand side. You just bring this term to right hand side. We will get this equation. Now integrating on both sides with respect to volume. So we will have this expression. So this is the final expression now, 1.68. Now we know that using equation 1.61. So we have now dp by dt, which is equal to partial d by dt integration p of r comma t d tau, which is equal to this expression. Already we know this. This can be combinedly written like this. Combinedly we can write this. This is exactly left hand side of equation 1.68. See here. So this is exactly equivalent to left hand side of equation 1.68. So this can be replaced by partial dp by dt, which is equal to psi star d psi by dt plus psi d psi star by dt. So instead of left hand side, we can write dp by dt. So this is dp by dt, which is equal to this right hand side. We have not disturbed any term on the right hand side. Now let us consider this expression. Del dot psi star del psi minus psi del psi star. You consider this expression. Now we differentiate with respect to x. So as I said earlier, keeping this as constant, you will have to differentiate, plus keeping this as constant, you will have to differentiate. So first we are going to differentiate this. So this becomes del psi star, keeping this as constant, plus you just keep psi star constant, you are going to differentiate this. This becomes del squared psi. Similarly, second term of this expression goes minus del psi star minus, keeping this as constant psi. We are going to differentiate del psi star. This becomes del squared psi star. Now there are four terms. Look at the first term and third term. Look at the first term and third term. See here we have both the terms are similar. Only thing is we can interchange. Say psi star psi is nothing but psi star. Similarly, del psi star del psi is nothing but del psi star. So we can cancel these two. We can write second term and third term, fourth term, and exactly like this. So the right hand side becomes exactly like this. Now, so look at this equation. This right hand side of 1.68 can be replaced by right hand side of this equation. So this becomes partial dp by dt, which is equal to minus h bar divided by 2mi integration your del dot psi star del psi minus psi del psi star. So we have considered this term. So this can be replaced exactly by this term. From Green's theorem, this volume integral is converted into surface integral. So d tau becomes now dA. So dp by dt, which is equal to minus h bar divided by 2mi integration over a psi star del psi minus psi del psi star dA. This term, just look at this term right hand side of equation 1.70 is known as current density, which is defined as J of r comma t, which is equal to this term. Now look at whether the unit matters or not. We will find out. We know that the square integrable function is equal to 1 according to normalization constant. Now you substitute here. What is the unit of psi here? Psi must be 1 by root L. Only then this will become 1 by L. Already dx has a unit L. So L will get cancelled. We have answer as 1. So your psi will have unit of 1 by root L. Now psi has a unit of 1 by root L. Psi star also will have 1 by root L unit. So you have 1 divided by root L. What about your del psi? Del psi has a unit of d by dx. So this will have 1 by L. Psi has a unit of 1 by root L. Root L and root L will have L. L multiplied by L will have 1 by L square. So this term bracket in bracket, this term which is in the bracket will have the unit of 1 by L square. Now come over here. H is the unit of m L square t power minus 1. And here this m and this m get cancelled. So we have L square divided by 2. L square divided by t. So this multiplied by 1 by L square will give us 1 by t. So it means right hand side has the unit of 1 by t, which is nothing but you compare with the left hand side, we have probability per unit time. So it implies that this is exactly matched to the unit. Now dp by dt, which is equal to minus j dot n cap dA. So by Gauss divergence theorem, again this can be converted into volume integral minus div j d tau. So this becomes partial dp by dt plus, so volume and d tau will go up. We have div j equal to 0. This equation 1.73 is known as law of conservation of probability or continuity equation, and it is analogous to the equation of continuity dp by partial dp by dt plus div j equals 0 of flow in hydrodynamics and electrodynamics, where rho is the fluid density. So here it is d rho by dt plus div j equal to 0. So where rho is the fluid density. So that's a mistake here. It is not dp, it is d rho by dt, where rho is the fluid density. J of r comma t is the probability current density at the point and the time. It represents the change in probability density due to probability current density. Now let us take the expression for the current density now. So J equals H divided by 2 mi psi star del psi minus psi del psi star. Now just take the real part of the quantity which is inside the bracket. So J equals real part of psi star H divided by mi del psi. Now H divided by mi del, you just take this expression. We know that the operator P can be expressed as minus IH cross del multiplied divided by I will give you H divided by I multiplied divided by I. So I squared, already one minus is there, so this will become plus. So H bar by I. So H bar by I del. So here H bar divided by I del is nothing but your P. One M is there. So this represents P by M. We know that P equals MB. So P by M will give you velocity. So it implies that H divided by mi del is nothing but velocity operator. What is the remaining term? Remaining term is psi star psi. Psi star psi is nothing but probability density. So H divided by mi del is nothing but velocity operator. The remaining term psi star psi is nothing but probability density. The product of these two is nothing but probability current density. So current density corresponds to the product of velocity and the density of probability. It implies if the probability of finding a system in some region increases with time, the probability of finding the system outside decreases with the same amount. The increase and decrease of the probability arise because of change in psi with respect to time. When the volume is so large so as to contain the particle with a certainty corresponding to the total probability of 1, the surface is at infinity. So it implies that del dot j equals 0. Then the probability density is constant in time. Such states are called stationary states. So therefore, limit tau tends to infinity, where del dot j becomes 0. So it becomes partial d by dt integration psi star psi d tau equals 0. It implies that the total probability is conserved. Further, it is noticed that the normalization of the wave function is also time independent. That is, once we have normalized the wave function, it remains normalized for all the time. Now let us try to solve one problem. Consider a wave function of a particle psi of x comma t, which is equal to e power ikx minus omega t. The first division is the wave function is eigenfunction or not? We are going to find out. The second division is, does this represent the ground state or not? And the third part is, obtain the probability current density of this function. The first one is whether it is an eigenfunction or not. Here, the wave function depends on both x and t. So now we are going to differentiate with respect to x. We are going to differentiate with respect to time. When you are going to differentiate with respect to x, that will give us always momentum. When you are going to differentiate with respect to t, with the multiplication of IH will give us always E, energy. So minus IH cross d by dx. This is your momentum operator. The expression for momentum operator is nothing but minus IH cross del. So minus IH cross partial d by dx e power I kx minus omega t will give us, with respect to x, we are going to differentiate. So when you are going to differentiate with respect to x, that will give us ik. Already one minus IH cross is there. So we have minus IH cross ik e power I kx minus omega t. So this becomes I into I squared minus 1. One minus is there. So this will become plus. So h bar k e power I kx minus omega t. Now this is the eigenvalue equation, like h psi equal to e psi. So here it is p psi equal to h bar k psi. See here, this is the expression for your momentum operator. So p psi, which is equal to h bar k psi. So h bar k is nothing but eigenvalue of the momentum. For energy, we have IH cos partial d by dt e power I kx minus omega t. So when you are going to differentiate with respect to t, so that will give us, we are going to differentiate with respect to t. So that will give us minus I omega. So IH cross multiplied by minus I omega e power I kx minus omega t will give us h bar omega e power I kx minus omega t. Now, energy operator E operates on psi will give us the eigenvalue h bar omega of with the function. And look at the wave function on both sides. Both are equal. So surely the given function is eigenfunction. And h bar omega is the eigenvalue of the energy. H bar k is the eigenvalue of the momentum. Now we will come to the second part. Energy here, the energy of the bound state is positive here. See, energy of, here it is positive. Energy of the bound state is, if it is usually negative. Here the energy eigenvalue is positive. Hence it is not a bound state. See here, we have positive value. Suppose if it is negative value, then we can say that energy is a bound state. For example, when you take hydrogen atom, the bound state of the hydrogen atom is nothing but, binding energy of the hydrogen atom is nothing but minus 13.6 electron volt. So it's a bound state. But here it's a positive value. So it is not a bound state. Now third part. The expression for the current density is given as J equals I get star divided by 2m psi del psi star minus psi star del psi. Here I have changed into psi star del psi. See here, earlier expression goes like this. You have see h bar divided by 2mi psi star del psi minus psi del psi star. I have changed this one as multiply divide by I, and I have changed this one with a minus sign. So that's the reason both the equations are the same. Both the equations, the previous one and this equation are the same. Now we know that psi is given us this expression, and you are going to differentiate with respect to x will give you this d by dx e power I kx minus omega t, which is equal to ik e power I kx minus omega t, which is equal to your ik e power I kx minus omega t. Now take the complex conjugate. So when you are going to take the complex conjugate, as I said earlier, I becomes minus I. So e power minus I kx minus omega t. Now again differentiate. When I want to differentiate with respect to x, that will give you e power minus I kx minus omega t. That will give you minus ik e power minus I kx minus omega t, which is equal to minus ik e power minus I kx minus omega t. So now substitute for psi del psi star psi star del psi. We will have this expression. Now e power I and e power minus I will get cancelled, and remaining term will be minus ik. Here too, e power plus I kx minus omega t, e power, here there's a mistake here. We have psi star, here it is minus. So here it is minus. See here it is minus sign, and this minus sign and this plus sign will get cancelled. See here it is minus sign, this is plus sign will get cancelled. You have here it is, you have minus ik again. Already you have minus ik. Here also we have minus ik. This becomes minus 2ik. This 2 and this 2 will get cancelled. As I said, as I into I multiplication will give you I squared minus 1. So minus minus plus. So remaining term will be h bar k divided by m. So the expression for the current density is h bar k by m.